this morning. And as usual, we have a nice plan. We're going to discuss some general concepts around these topics, and then we're going to be specific on 3 specific distributions, and at least one of them I'm sure you have met previously in life. And then we'll go a bit general at the end again. Before doing that, let me just motivate it. If you didn't get the idea, I hope you did, and I think many of you will have done. In the CampusNet, there are a number of nice stories and links. For instance, this one. This is a report from Sundhedsstyrelsen some years back, just to make a little point here, that this course is about looking at data, analyzing data, understanding our data in the right way. So why do we suddenly discuss throwing a coin or throwing a dice that we're going to do today? Well, because, for instance, look at this. These are the percentages, the proportions of children born in Denmark with different sorts of handicaps, in Danish, misdannelser. From very mild ones that many of us might have to quite severe ones. It's around 4 or 5% actually. It's a pretty high risk to have a baby. These are only even among those that survived. Not to scare you, but that's how it is. Now, looking at such percentages from year to year, we have to start thinking about how do we look at those in an intelligent way. What is the link to my story today? The link is when we look at 70,000 births in 1 year in Denmark. That's around the number, at least back in those days, probably not changed a lot. That corresponds to 70,000 coin tosses. Coin tosses, right? With, when we view it this way, 2 possible outcomes. Success or failure, right? Handicap or no handicap. Counting only the survivors. So, when studying such proportions, such numbers from year to year, we have to realize that these are the outcomes of a random phenomenon out there that behaves like throwing a coin. Many times, of course. That's the binomial distribution. We're going to recap that today. Many of you have met it before. So it's just to make it very clear. The reason why I talk to you about these distributions is because I want to make you able to look at such numbers in the intelligent way that these distributions will make you able to do, right? So we should realize how does a binomial system behave in order to understand what is the information of such data really. Is it really increasing or is it just random or whatever? So these probabilities are important for us to be able to do the intelligent data analysis, which is the definition, my definition of statistics. So let's get moving. Very generally, random variables. So we're going to use this time and next time in talking about probability only. That's basically something that sometimes has one value and other times another value, very loosely speaking. It's kind of a model also for the system or for the experiment, as we use the word here. So we can talk about it even without having done it, really, right? So we can talk about a concept without actually doing it. It could be throwing a dice, could be all sorts of things, measurement in the blood also. And that's why we have 2 days, because we distinguish, and we have to, from a mathematical perspective, we have to distinguish between the discrete and the continuous systems, and the discrete and continuous phenomena, right? Discrete, that's when we can count something. For instance, throwing a coin, right? Heads or tails, success or failure. There are only 2 possible outcomes. That's pretty easy. If you throw it 10 times, there are 11 possible outcomes. But it could also be counting something, the number of planes departing within the next hour somewhere. It could be anywhere from 0 to a transillion or something like that. Probably unlikely with a transillion if something is called like that, I don't even know. But there is no sort of in the system natural upper limit for it. It could also be continuous, sorry for the Danish word there, Wind speed, transport time, blood measurements. We distinguish. It's not going to be a big issue for us in this course. But if you want, when we write about it in the notes and in the books, we have to try to be precise. So we distinguish between the capital letter random variable and then the outcomes of it. Or sometimes we are going to talk about a sample or the realization or the observation. We denote that by small letters. For you, that is not going to be a big issue. It's just an explanation to how to read our notes. So let's get started a little bit with the sort of the example we're going to play around with. For instance, simulating or thinking about, let's say, throwing a dice, 6-sided dice. Let's try to see. Let's do it, and then let's get back to this. Now I'm going to, today and next time, I am going to use R in a kind of a pedagogical way, not so much data analysis way. I mean, you may judge whether you find it pedagogical, but the purpose of it is not necessarily to teach you to do data analysis with R today and the next time, but rather I'm showing you how we can use R to simulate those random phenomena that we are using the probability distributions to model and handle for us, right? That's a nice thing about it. Would take a long time if I asked you to bring on some dices and do 100,000 dice throws. That would take a long time for you. It's much easier to let the computer do it. For instance, there's a nice function in R called sample that can take a random number between 1 and 6. Let's see. I didn't cheat. It's not 6 all the time. 5. This is like throwing a dice. Still a bit... Whoa, sorry about that. We could also do it 30 times in a row, easily, like that, right? Let's sample 1 to 6, 30 times, and we take with replacement, meaning that we each time take one of the 6 and one of the 6 and one of the 6. So we take each time from that. Let's see what happens. Like that. We could also look at the table and say 1 round of 30 throws of a dice would give me 6 1s and 4 6s. Next time, of course, I would get something differently. Let me just do it again. 8 1s and 2 6s only this time, a bit less good if we wanted 6s. Now to the point that I was going to get at, we could also plot, of course, the proportions of 1s, 2s, 3s, 4s, 5s, and 6s. And then I could plot what I'm going to teach you now, what is known as the probability density function, a fancy name, but of something quite similar in this case, namely the name of this underlying probability that I think all of us would know and think about, that we would expect there to be 1/6 of probability of getting each of the individual outcomes. That has the name, this mathematical construct is called the density function. Formally, it is the probabilities, like this, of the random variable that describes the system we're looking at. So it's still quite general in a way. We use the dice as an example here of a general concept. And here are the density function by definition. Any function, if you want to go mathematical about it and sort of quite general about it, any function adding up to 1 with only positive or 0 numbers could act as a system for probability outcomes. That's one way of saying it. So it need not be the sort of 1/6, 1/6, 1/6 case. It could be something else, and we'll see that in a second. actually, we already started this also. If we only threw the dice once, of course, we wouldn't, from the outcomes, know a lot about the distribution, because that's what's going to happen in statistics. So it may be confusing, but I will maintain trying to make the link to statistics, because you could discuss probability theory without talking about statistics. But this is a statistics course. In statistics, it's very much that we are looking at the data, so we would maybe sometimes look at the data to get information about these probabilities. If we would not be able to sort of define them theoretically ourselves, we would look at the data to get the probabilities. So we need some samples to be able, if we didn't know whether the dice was a cheating dice or something, and someone gave you the dice, what would you do? You would start throwing it many times, and then look at the outcomes, to look at the distribution. That's the idea. And here's the slide showing the R code that I was just running a second ago, where I simulate throwing a dice 30 times by use of R. Right? So I just use the R instead of spending the time doing it up here. So we jump to the next example.